Hello everyone, it's Shuriken255 and now it's time for the 5th devlog of the Zozo game's development. For the past 3 months I have been working on the animation support for the game, and by the way, all visuals for this devlog except screen recordings are compiled into a single animation file and rendered inside the game itself to showcase its capabilities as well as to help explain challenges that I have encountered while developing this animation tool. I will mostly be using this animation tool to make fully animated boss fights for the game, and I anticipate that animating these boss fights will take the majority of the entire game development process. So I decided to make the workflow of making and transferring animations to the game as smooth and easy as I can. I evaluated a lot of options to make animations for the game and decided to go with Adobe Animate. Despite my abusive relationship with Adobe Animate, it has a lot of features that I need and other softwares don't provide, one of them being timeline nesting system that most Flash users know as symbols. Animating an entire boss fight without this feature would be very painful, and I have not seen any other software that supports something similar. So let's talk about the features the animation in my game supports. First of all, my animation supports both raster and vector graphics. The difference between these two is that the raster graphics are stored as array of pixels, while vector graphics are stored as, well, vectors. The vectors may be transformed and rendered onto a raster canvas after these transformations. That's why vector graphics work so much better than raster graphics when it comes to transformations on a low-resolution canvas, because when you try to transform a raster image on a low-resolution canvas, it produces horrible artifacts. Making vector renderer in Love was a tricky part. First of all, everything in Love is rendered by GPU, and I don't have a direct access to RGBA data to efficiently edit it. Therefore, the vector rendering logic should somehow be moved to GPU as well. I did not write any complex shaders before, so for me it was a new experience. The first problem I encountered is sending and storing a large amount of vector data in the video memory so the fragment shader can access it when rendering the graphics. The uniform vector arrays on my laptop have a limit of 512 elements, and sometimes I had more vectors than that in a single shape, so I had to get creative. To explain the solution I came up with, I first need to explain how vectors are represented in my graphics renderer. To be honest, calling them vectors is a little bit inaccurate in my case, so I'm going to call them edges from now on. First, let's draw the bounds of a shape we are going to render. The top left coordinates of these bounds will be 0, 0, while the bottom right corner will be 1, 1. If we add an edge inside of these bounds, each coordinate of its points is going to be in range from 0 to 1. We can build any complex shape out of these edges. The only one thing, the edges have to be straight lines because my renderer does not support curves. So each of these edges can be represented by 4 numbers, x and y of the first point, and x and y of the second point. So at the end, to store information about a single edge, we need 4 numbers that range from 0 to 1. And what type of information in GPU that is a large group of 4 numbers that range from 0 to 1? It's texture data. Each pixel of a texture consists of red, green, blue, and alpha components, so we can store all information about the edge in a single pixel. And also, texture data can be accessed by the fragment shader. The way my renderer does it is by storing xy of the first point in red and green components, while storing xy of the second point in blue and alpha components. If we increase the red component of the pixel, then the first point of the edge is going to move to the right. If we increase the green component, the point goes towards the bottom. If we increase the blue component, then the second point moves towards the right, and if we increase the opacity of the pixel, then the second point goes towards the bottom. We can guide the fragment shader where the edge data of the specific shape starts and ends in the texture with uniform variables, as well as provide other crucial information like the color of the shape and the edge data texture size. If you are interested in how edge data looks like as an image, this is an image generated from the edge data of the visuals from this video. Yep, it looks like random colors with random opacity. And also, if you are wondering how I render vector graphics based on the edge information, I use a scanline method. Long story short, when you draw a pixel, you start a ray from this pixel pointing to the right. Then you check how many edges this ray intersects. If the number of intersections is even, the pixel is outside the shape and must be discarded. If the number of intersections is odd, it's inside the shape and the pixel must be painted. As I said before, I don't have a lot of experience writing complex fragment shaders, so my shader is a bit of a mess with lots of branching that yet has to be replaced with vector math. The first time I tried to render Zozo with my vector renderer, he looked like this. It took me a few days to find out what's wrong. The GPU stores pixel data as RBGA and not RGBA, so all I had to do was to swap two letters in my shader code. Wonderful. As I mentioned earlier, my animation also supports raster images. Rendering vector graphics on a low-resolution canvas may be unpredictable, and in many cases you want to have more control over the final result. Yet, the style of animation I'm going for will be hard to make in the pixel animation software alone, so I decided to initially animate in Adobe Animate and make a plugin that converts this animation into a sequence of PNG images. Then I import this PNG sequence into Sprite, adjust pixels, and export it as a sprite sheet. To import this sprite sheet back into Adobe Animate, I wrote another script that reads JSON data generated along with the sprite sheet in Sprite to assemble animation back in Adobe Animate, so it can be included on export. Other feature my animation converter supports is symbol nesting. You can put symbol inside a symbol inside another symbol as many times as you want, and the hierarchy of the symbol structure will be saved in the exported file. The other feature that is fully supported is classic motion tweens. You can set rotation settings, classic ease, easing methods, custom easing curves, or even have different types of easing settings for each property. Also, the animation converter fully supports Adobe Animate's color transforms and can handle nested color transforms as well. I also managed to add mask support. I did not plan to do it at first, but I have recently discovered the existence of stencil buffers, and I really wanted to try to mess with them, and masks seemed like a very good opportunity to do so. So, let's talk about how do I transfer files from Adobe Animate to Love. When I started working on the animation support, I initially used GSFL script to export all required information from the FLA file into an auto-generated Lua file, along with SVGs of all shapes required to assemble this animation in the game. Then this Lua file and SVGs were fed to the converter made in Love to put all of this information into a single binary file. The animation library that I made for this game will then read this file and recreate this animation in the game. The problem with this approach was the speed. GSFL scripts are incredibly slow, and it takes a very long time to export SVGs for every shape. If I would have to convert a finished boss fight animation with tens of thousands of shapes in it, it could take over 10 hours. So I had to figure out a faster approach. When I was working on the nuke effect in Animation vs. Coding by Alan Becker, I had a similar issue that letting GSFL script to insert all the numbers will take an unreasonable amount of time. That was the time when I discovered that Adobe Animate stores all information in human-readable XML files that are packed into a zip folder with FLA file extension. Renaming FLA file to zip would allow you to extract it as an archive with some warnings, and packing the extracted content back into a zip archive and renaming it back to FLA would produce a fully functionable FLA file. This way I was able to inject the numbers animation into an existing FLA file in 10 minutes instead of having my laptop run a script for several days. So it made me wonder, can I just grab all information about FLA file purely with Love without using any GSFL scripts? After some time researching and looking into extracted files, I figured out that yes, it's absolutely possible. All I had to do was to write a series of commands that will duplicate the FLA file, rename the second FLA file to zip, use 7-zip to extract the contents of the zip into a temporary folder, read all required files from this folder, and then remove all the files that were created in the process. After that, the information read from these files is being sent to the converter made in Love to produce the final animation file that will be read by the game. This approach was over 100 times faster than using GSFL scripts. The most problematic part of making this new converter was vector graphic extraction. SVG files store shape contours separated by color, which was much more convenient when exporting the animation file. FLA files store shapes as borderline segments. These segments are separated depending on what colors the border separates. For example, SVG would save this image as 3 shapes, it's just the blue one would have 2 contours. The way it is saved in FLA file is 6 separate borderline segments. It took me around 2 weeks to decode the way the shapes are encoded in FLA file, create an algorithm that would read this data, sort these border segments by color, and then reconnect them back into looping segments similar to the way it's stored in SVG files, while also debugging weird edge cases that popped up during the algorithm implementation process. But I also was able to very efficiently convert curves into multiple straight lines during the conversion process. The amount of lines is decided depending on the curve itself and the smoothness parameter that is set in the converter. So let's finally talk about the animation file. As I mentioned before, all animation information is stored in a single file. It uses a self-made format that I designed specifically for Zozo game. I called it ZEF, which stands for Zozo Animation Format. ZEF files are binary files that were designed to be very small. The size of the file that has all visuals included in this video is barely 200 kilobytes. I won't go into details on what techniques I used to compress the file, but I spent a good portion of time thinking how to make this file very size efficient. The next thing I'm planning to do with the animation converter is to be able to include meta information, like level geometry, hitboxes, camera, sounds, and more, but before I can do that, I must finally implement the level environment and basic game mechanics, which is going to be my main focus until the next devlog. If you want to know more about Zozo Games development, you can join Zozo Games Discord server. The invite link to the server is in the description. That was it. I hope you found this devlog entertaining. See you later and have a great day.